Bismillah ar-Rahman ar-Rahim. Assalamu alaikum. How are you, Shabab? Today, inshallah, we'll talk about position measurement. Here, we'll not talk in that details or the deep details. Just we'll take the summarize or the simple concepts about the position measurement. It is very huge, anyway, very huge subjects. But here, just we'll take the headings: absolute position and incremental position. So this is to talk about her position. The difference between these two things is that the absolute position, it has fixed reference. The incremental is not fixed point reference. This is the difference between them. Fixed reference, if you measure the distance respect to fixed reference, this is the important word, fixed. That means you will take the absolute position. If you are measuring the change in the position but not in a fixed point or fixed reference, that means you are taking the incremental position. Okay, how that? For example, this is my reference here. This one, my reference here. This triangle is my reference. Now, look here, Shabab, to this angle. To this angle. Type. If I take the distance from here to here, based on this reference, this means I take the absolute. Let's say, for example, 3 meters. So that's from the reference, fixed reference, until the edge here, I have what? 3 meters position. The position is at 3 position. So at 3 position. But if I take this length, 3 meters, similar to that one, but this one does not have a reference like this one. So 3 meters depend on what? Depend on your choice. For example, from this location until this location is 3 meters. This is the position. If I might take this as a reference, it has a reference, which is this one, but it's not fixed. Sometimes I will say this one the reference. Sometimes I will say no, this is the reference. Sometimes I say okay, in the middle here, between them, this is the reference. So the position for this edge from this reference is 1.5 and this one 1.5. So here, this one here that I have it here, it has incremental position, but while this one, it is the absolute position, because here a fixed reference. Here there is no fixed reference. It can be varying, can be sometimes here, sometimes here, sometimes here. So both of them, they have reference, but one of them, it has fixed reference, constant reference, does not change its location. The others, it has a varying reference point. Type. Return back here. Rectilinear motion. It is a linear, but when I say rectilinear, that means it's a straight motion. Linear motion also, it is a linear motion, but it's not necessary to be straight. It's possible to be curved, move in the curved way, not in the straight. But if I say a motion in a straight movement, يعني خط مستقيم, we call it rectilinear. Linear, it is also a movement, but in possibly it can be a straight line, it can be curved line. Difference. This is the difference between them. But both of them is linear motion. Angular motion here, it is the measurement of rotation. طيب, لاحظوا شباب here. Motion, when I talk about motion, that means I'm talking about the change of the speed, of the location, distance. Motion, look at the change in the distance, or the change in the acceleration, شباب, and the speed. So when I say motion, that I'm measuring the rate of change. لاحظوا, if I say rate, this word rate, that means I'm talking about time. So if I say rate of change of the distance per time, I'm talking about speed. If I say rate of the speed respect to time, that means I'm talking about acceleration. Anyway, if I mention the rate of something, that means the measurement of these things respect to the time, unless if I specify another reference, not the time. For example, if I say the flow rate, that means how much volume pass per what? Per time. If I say speed, that means how much distance per what? Rate per what? Per time. But if I say density as example, it is the rate of what? It is the change or the amount of mass respect to the volume. Here I don't put rate here. I just write density or ratio between mass and volume. I don't mention rate, I say ratio between mass and volume. So this is the difference between word rate and ratio. Now return back here. If I say rectilinear motion, that means in straight lines. Either measure the speed or distance, change the time. The same thing, angular motion, it is also either measure the distance or the speed, change the time. But then this one is angle, and this one is what? Linear. So if I say velocity length over time or acceleration, it is v over time. This one is linear. Angular acceleration, it is omega over time. Omega here is that angular speed. So also angular speed, I can say also it is what? It is what? Angle, which is okay, so theta per time, the angular speed. So this is the difference between them. All of them are motion, but the first two things are linear and the others are angular. طيب, arc minutes. When we talk here about arc minutes, we are talking about a part of the angle. So the minimum degree is 1. As example, see here, 100 degree, 120 degree, and 55 minutes. This is the arc minute, shabab. This one that I mean arc minute. And 45 too, it is also arc second. So I have 3600 second per degree and 60 degree minutes per degree, arc minutes. هنا arc second. So this is the meaning of these things. But velocity or speed, we mentioned it already. Acceleration, we already know it. Vibration is a measurement of periodic motion about fixed reference point. So here we talk about absolute position. Also, it can be also the shaking that happened because of the process due to sudden pressure change, shocks, unbalanced things. Of course, this one unwanted behavior. It is an unhealthy case. Doppler effects, frequency change based on the objects. So I will send a certain sound waves to a certain object and it will reflect. The possibilities here that this movement or the movement of this object, it will change the frequency rates of the reflected one. So when I send the frequency to the subject and it collide to the subject, it reflects from this subject to me with different value of frequency. We call it this one Doppler effect. If I measure the difference in the frequencies between the one that transmitted and the one that's reflected, I can know how much the speed is running for this subject. This is the difference. Okay, now just go quickly to the devices that you use to measure the position. Okay, one of the devices, potentiometers. It is a convenient method of converting displacement in a sensor to electric variable. طيب, potentiometer. The working principle of potentiometer, it works on the change in the resistance of wire, which its length is changed, either it rotary or linear displacement for the voltage. Then can measure the position, either angular or linear position. طيب, here we know that the distance here, the resistance here measure angular position or linear position. That means varying the resistance, and also resistance will leading to varying the voltage. If I take the voltage here between these two things, between A and C, it will give me different values depend on the location of this rotating Weber shaft. So that means I will change my resistance. As you see here, maybe you can put it here. This is the resistance. One of them is linear, and this one the rotary. Rotary one, it can varying but in angles movement. Here in this one in street movement. If I take the resistance between A and C, it will varying depending on the indicator where it is located. 10, 30, 50, 70. The others also between the location of the rotating or Weber, rotating Webers. Either can 30, 40, 50 and 7 and so on. The A and B resistance are very huge. Of course, just applying force source between these resistance and measure the difference between these 2 points, which is A and C, I can find the varying in the current depend on my change in the resistance. So I will connect this movement part to my device in order to measure its position. Simply like that. Other devices, linear variable differential transformer. It is also another one used for small distance measurement, and you can say it is alternative the potentiometers. And inshallah I will talk about it more details later. طيب, light interference laser. Here we used here very accurate incremental position measurement. لاحظوا incremental. That means I need to define the reference every time. If I run the system, I need to define a new reference points in order to calculate my position. طيب, he said that monochromatic light single frequency can be generated with the laser and collimated into narrow beams. This beam reflected by mirror effect to the movement effect on the moving objects, which generate interface fringe with incident light as it's move. طيب, just here we know that light interference laser, we can measure the very accurate positions using that. Ultrasonic, infrared, laser, microwaves, these things also can be used for the distance measurements, like our system here in the police, traffic police, Sahar. They use it with radiation. The time for pulse of energy travel to object and reflected back to receiver is measured. From this one we can know the distance. Hall effect sensors. It's detecting the change in the magnetic field strength by using closed approximator toward the movement part. As you see here يا شباب, Hall effect. As you see here the Hall effect. The idea here, two magnets, and there is a magnetic field between them. If I insert a metal between them, or electric conductor between them, is necessary be metal يا شباب. It can be semiconductor. طيب, then connect there is electric cable with a certain source. Then I want to measure the other terminals part, the other here, other edges here يا شباب, and I want to measure the voltage between them. If I create voltage or the current here from the negative, or here the electronics movement, and of course the current will move here from the positive to negative, as you may remember that. But because the effect of this electromagnetic, there is some scattering potential, so it is creating a potential difference here, and I can measure it by the voltmeter. It can be also very small measurement يا شباب. As here is يا شباب, it just give me here small micro voltage. Then I can amplify it using the amplifier, high gain amplifier. It will give me analog output. And also I can change the saturation by that call it Schmidt triggers amplifier. It is developed with certain different design, then it gives me the digital output. So I can use this idea in order to measure my movement of the parts. For example, this one as a wheel speed, I want to measure its RPM, rotation per minute. Just here put my sensor here, Hall effect sensor, and behind it there is a permanent magnet, and there is a magnet field. What happens? Trigger wheel will move. Of course, there is a gap between the wheel and this sensor, of course. And by this change, when the head or the tips of the wheel increase, it comes to when the wheel comes, the tips of the trigger wheels going around the sensor. Of course, the magnetic field will be changed here, and it will give me the pulses, as you see here, just pulses. That means there is increment in the magnetic field, and if the sensor will detect it, and it will give me the change in the signal. Magnetoresistance element. Magnetoresistance element. It is also a new technology used to measure the rotation or the position by changing the magnetic effects on the resistance. It is alternative to the Hall effect of device. Say the change here will be in the resistance, not in the magnetic field. Sorry, not in the potential, which is here resistance change, not the voltage. The voltage change. طيب. How it's work? It's detecting a magnetic state that proceeds by electric circuit. طيب. It's really consists of the sensor here consists of three layers. Three layers, or the magnetic layers. Space layer, sometimes they call it the bend layers here, and they call it the bending layer. The bend layer here, layer here is it's the layer that has a fixed magnetic, while the free layers it can be changeable. So if I change, the polarity will change here. That means there is no resistance. Here you increase the resistance. Now low resistance, same magnetization direction. High resistance, opposite magnetization direction. See here, the lower one is fixed, does not change. The bend layers. When you increase the resistance, that means high voltage, low voltage. Decrease the resistance means the high voltage. So I can use this application for different purposes. Switching, as you see here previously, just up, down, something happens, come nearest, something reset up, it becomes what off. Or encoding, in order to count the rotations by just changing the polarities, and of course the magnetic field will change based on this polarity change. Or the linear movement, just here, and that's all. You will measure the linear movement, how much concentration of magnetic field comes near to the sensor, or how much was far from the sensor. Angle, also changing the angle polarities, all it affect in my angle of the magnetic field. طيب, here really this one, this magnetic sensor, it has advantage more than the Hall effect. Hall effect, we remember that it's a magnetic change, it's the potential change regarding the magnetic field. So magnetic flux will enter and the Hall effect will happen. This will be happens. See the detectable area here, it's a little bit small compared to that, to the MR sensor, or magnetic resistance element sensor. Another benefit also, if you see here يا شباب, if you take the measurement for them, the hysteresis and the Hall effect or can say that there is a hysteresis element for the AMR, showing that it can give you higher power output. Regarding the compared to the HAL, see the threshold effect on it, on off. See, the power is a little bit small compared to this one. So here is the signal to noise ratio, it is a little bit here higher. طيب here is sensitivity variation than the HAL sensor effects. طيب see, high voltage, low voltage here, high voltage, low voltage because of the high resistance. You will make that change that resistance with you. High resistance, low resistance, opposite the voltage here. Switching, as you see here. The resistance here high, that means low voltage. If the resistance very low, that you receive high voltage. So I can play in the resistance movement here. Also, you can put single pole, single output, or double pole, single output, or double pole, double output. See here, Shabab, this is the output here. If you say single pole, that means when the switching comes, this low voltage will give me output, and the high voltage will give me. But when you change the polarities, no effects. This is the single pole, single output. Just only one polar side will affect will give me the results. But if you go to the double pole, single out, whatever the change in the polarity, just a change in the sign, but you'll give me output. Will give me what? Output. Change the polarities, so it gives me a voltage, but different sign, minus sign, as you see here in these drawings. طيب double pole and double output, if it is one side polarity, it gives me one output. If it changes the polarity, it gives another output. This is also another benefit of using this one. So this is the flexibility of MR. This is the flexibility of MR. This is the sweetness of it. You see here, you can also use switching as the linear movement. How much distance? What will be the linear distance here? Also, you can utilize it for encoding. As what? Encoding. So as to encoder, if you set rotate, it will change the polarities. North, positive, south, high with the south, low with the north. High resistance with the south, low resistance with the north, which means high voltage in the north, low with the south. As you see here, this is also one of those methods for encoding. Also, you can play with that as phasing. You can change the phasing based on this one. See this, the same orientation of the magnetic here, this fixed one. Right. You can also play with these things. Also, I can change the angle. The polarity change means polarity changing the angle, and also I can measure the angle measurement change here. So this is the benefit of using this type of magnetic resistance sensor. Optical devices. It can detect the motion by sensing the presence or absence of the light. I will show inshallah after a while a video will explain the use of the optical devices. How can utilize them in measuring the movement. Okay, power laser, it can also be included in the optical devices. They are used for scraping or and machining of metals, eliminating, and that's all. Type accelerometer sensor speed, it change the measuring force that regarding by the change in the velocity by changing and this measurement using the mass change, and the mass change movement mean acceleration movement, we call it seismic mass change. This device can made with the cantilever's mass and strain gauge to give us the change the techniques or the change in the acceleration. Different technique, either capacitive measurement or by the strain gauge measurement. So I will connect this mass, seismic mass, to the strain gauge or to a capacitive measurement techniques. Then by changing the mass, acceleration, the strain will affect either tensile, as we remember that يا شباب, and the force measurement, either tensily or compressing the strain gauge. The same thing, either compressing the capacitance, reduce the capacitance, or decrease or increase the capacitance of sensor based on the increment or decrement of the acceleration of the seismic. And this seismic mass will be connected to that device, measurement device. Vibration sensor, it is also used as acceleration device to measure the vibrations. Inshallah, I will try to, if you have a time, we'll take more detail for this vibration sensor. طيب, now it's remaining now, there is a video here. It's helpful and very nice. It clarifies the meaning of the encoders, what you call it, the position encoder. Listen to this.
An encoder is a device that is used in many industries to provide feedback. In the most basic terms, an encoder, regardless of the type, which we will cover later, senses position, direction, speed, or counts. Encoders will use motion under a variety of technologies and translate it into an electrical signal. That signal is then sent back to a controlling device, such as a PLC, and is interpreted, meaning scaled, to represent a value that will then be used within the program. Some of the technologies involved in encoders are magnetic, mechanical, resistive, and optical. Optical is the most widely used encoder motion translating technology. There are different types of encoders, such as absolute and incremental. We will describe those in greater detail in a future lesson. But for now, an example of an incremental optical type encoder uses a beam of light that passes through a disc that has opaque lines in a specific pattern, somewhat like the spokes of a wheel. On the other side of the disc is a photosensing device that will interpret the light based on the pattern on the disc. Picture a shutter blocking and unblocking the light. The pulses of light are then converted to an electrical signal to be sent back to the processor through the encoder's output. Encoders have a wide range of uses, which include closed-loop applications such as servo or VFD control, measuring, and counts. Here are some examples of processes that may use an encoder.
Variable frequency driver.
For VFD control, you may be running a pump on a VFD to fill a tank full of a liquid. You are requesting a certain speed and want to verify that the pump's VFD is at the requested speed. An encoder on the VFD may be used for feedback of speed. Next, let's give an example for a measuring process. In this application, you will need to cut some aluminum product to a particular size. You are passing a long roll, meaning hundreds of feet, of the aluminum sheet through a cutting mechanism. You need to determine the amount of aluminum fed so that you can cut the sheets to the proper size that will be used in a separate manufacturing process. An encoder, attached to the conveyor and reading the material that is feeding through your cutting assembly, will indicate the length of material that has been fed since the last cut. That feedback can then be used to adjust the cutting blade to sever the length required. For an example of counts, consider this process. You have a conveyor line that has bottles running on a conveyor. They are counted by a photo eye sensor when entering the assembly. They have a cap with an aluminum tamper-proof foil on top that needs to adhere to the bottle. Once the foil is sealed, the bottle will then move down the conveyor line and verified that it exited the cap sealing assembly via an exit photo eye sensor. Some of the requirements for this station are: the same number of bottles that enter the assembly must exit in a predetermined time frame. The bottle must not remain in front of an entrance or exit sensor. The bottle must not be exposed to the inductive sealer longer than a predetermined amount of time. You must make this assembly flexible enough to handle many types of bottles and entrance and exit sensor placement. Consider a prescription bottle. Easy, right? No handles, just a bottle that is a standard size. Now, consider an antifreeze bottle with a somewhat small cap and a very large handle. How in the world are you going to meet the requirements for the machine and remain flexible? If you put a pill bottle in, yep, easy peasy, right? Bottle in, seal, bottle out, no sensors blocked. If any of the requirements fail, bottle in, seal, tips over and isn't counted out, machine halts and alerts on operator of a malfunction. How about the antifreeze bottle? Bottle in, cap passes in front of an entrance sensor, bottle counted, then the handle. The system faults because it sees a blockage at the entrance. How do you tell the machine that this is expected behavior? An encoder, of course, and a selector switch for a setup mode. To set up, insert your product, in this case the antifreeze bottle. You make sure to feed cap first, and it must contain a foil. Your program reads an entrance on the sensor and records an encoder reading, as well as determines that this is a cap and records that fact. Your program then reads another entrance and determines that this is not cap and must be some other acceptable part of the bottle, possibly a handle. The single bottle continues down the line, where the exit sensor is triggered. At that point, you again record the encoder value. You now have an encoder count that registered at the entrance and exit. In the code, you subtract the entrance from the exit, and you have a bottle count. You now know precisely how long it will take that bottle to move through the system, meeting the must enter and exit in a predetermined time frame, in this case, encoder counts. You have also made the flexibility aspect of different types of bottles, as well as being able to place the entrance and exit sensors any reasonable distance apart. When back in run mode, the code knows that there's a handle to ignore when it comes into the process, and doesn't fault the machine. You register the encoder at each bottle entrance and predetermine when the bottle must exit. If the bottle doesn't exit the machine in a timely manner, which is based on your projection and the current encoder count, the machine faults. This is a great use of an encoder that is fully configurable. Count in, count out, subtract, done. We discussed what an encoder is and how it can be implemented in your application. In this video, we are going to discuss the various types of encoders and which encoder may be used for which function. There are many types of encoders, but they basically fall into two main sensing techniques, those being linear and rotary. Within those categories, there are differing encoder measurement types, such as absolute and incremental. There are also various electromechanical technologies, such as magnetic, optical, inductive, capacitive, and laser, to name a few. There is a plethora of information regarding encoders, and it may seem hard to wrap your head around it. Descriptions like rotary or linear, optical and magnetic, absolute and incremental. We touch on a few basics to help you understand what's what and why. Let's first break these categories down a little and explain a couple of the many configurations. First, the linear encoder uses a transducer to measure the distance between 2 points. These encoders can use a rod or a cable that is run between the encoder transducer and the object that will be measured for movement. As the object moves, the transducer's data collected from the rod or cable creates an output signal that is linear to the object's movement. As the distance is measured, the linear encoder uses this information to determine the position of the object. An example of where a linear encoder may be used is for a CNC milling machine, where precise movement measurements are required for accuracy in manufacturing. Linear encoders can be absolute or incremental measurements. We will touch on absolute and incremental measurements a little later. A rotary encoder collects data and provides feedback based on the rotation of an object, or in other words, a rotating device. Rotary encoders are sometimes called shaft encoders. This encoder type can convert an object's angular position or motion based on the rotation of the shaft, depending on the measurement type used. Absolute rotary encoders can measure angular positions, while incremental can measure things such as distance, speed, and position. Rotary encoders are employed in a wide variety of application areas, such as computer input devices like mice and trackballs, as well as robotics. Rotary or shaft encoders, as previously stated, may be absolute or incremental. The next encoder, which is a position encoder, is used to determine the mechanical position of an object. This mechanical position is an absolute position. They may also be used to determine a change in position between the encoder and object as well. The change in position in relation to the object and encoder would be an incremental change. Position encoders are widely used in the industrial arena for sensing the position of tooling and multi-axis positioning. The position encoder can also be absolute or incremental. Optical encoders interpret data in pulses of light, which can then be used to determine such things as position, direction, and velocity. The shaft rotates a disc with opaque segments that represent a particular pattern. These encoders can determine movement of an object for rotary or shaft applications, while determining exact position in linear functions. Optical encoders are used in various applications, such as printers, CNC milling machines, and robotics. Again, these encoders may be absolute or incremental. After explaining the main groups, you may be seeing a pattern. All the encoders basically do the same thing: produce an electrical signal which can then be translated to position, speed, angle, etc. Now that we have broken down the main groups, let's discuss the difference between absolute and incremental measurements. To discuss the difference between absolute and incremental measurements, we will use the rotary encoder type as an example. In a rotary absolute measurement type encoder, a slotted disc on a shaft is used in conjunction with a stationary pickup device. When the shaft rotates, a unique code pattern is produced. This means that each position of the shaft has a pattern, and this pattern is used to determine the exact position. If the power to the encoder was lost and the shaft was rotated, when power is resumed, the encoder will record the absolute position as demonstrated by the unique pattern transmitted by the disc and received by the pickup. This type of measurement is preferred in applications requiring a great degree of certainty, such as when safety is a primary concern, because the encoder knows, at all times, its definitive position based on the unique pattern produced.
Note here شباب, when he run the absolute encoder, it's running and it counted as binary code, The position here is certain and is known, well known. When he switch off the system, then return back to run the system again, the starting point, it is still known. It does not change. It is the same. So this one is absolute encoder. Okay, let us see the other one.
Absolute measurement encoders can be single-turn or multi-turn. Single-turn encoders are used for measurements of short distance, while multi-turn would be more suitable for longer distances and more complex positioning requirements. For incremental measure encoders, the output signal is created each time that the shaft rotates a measured amount. That output signal is then interpreted based on the number of signals per revolution. The incremental encoder begins its count at 0 when powered on. Unlike the absolute encoder, there are no safeguards regarding the position. Because the incremental encoder begins its count at 0 in startup or power disruption, it is necessary to determine a reference point for all tasks requiring positioning. In the previous video, when describing the use of an encoder for the purpose of counts, that example is a good example of an incremental encoder. Assume that the power has not been disrupted, and you have turned on the conveyor and placed the machine in setup mode. As the encoder is turning, the controller is receiving counts. Let's say the count range is 0 to 10,000. This is an incremental encoder, so the absolute position is not known. We just know that a full revolution of the shaft registers a count of 10,000. We'll place the object on the conveyor, and as soon as the entrance photo eye sensor detects the object, the current encoder count is captured. Let's say that number is 5,232. We will then capture the count with the object exiting and being detected by the exit photo eye. We'll say that the number is 6,311. So to determine the count of the full travel, we will subtract 5,232 from 6,311 and determine that the object travel is 1,079 counts. By this example, it is obvious that we do not know the absolute location of the object. We just know that the travel count from the entrance to exit is 1,079. That doesn't tell us that the object is 3 inches from the exit, just entering, etc. We just know that the object will enter, a count will be captured, and the object will exit, and again, the count captured.
Incremental. We don't know.
In the event that we did not see the object exiting within the allowable travel count, plus or minus a deadband, the machine will fault and the process will stop. There are many encoder variations out there, and we could go on for hours about the varying types. Hopefully, we have given you a basic understanding of what's out there, and when you may want to choose one particular type over the other.
Okay, this is the end of our lecture now يا شباب. خلاص we covered the as you mentioned يا شباب, only just simple or simplifies subjects. We don't go in the deep details. If we want to go to the deep details, it is really a huge subject, and really it's very funny, by the way. Okay, now the remaining is now, I think from now until the coming weeks inshallah, we will talk about devices in details, little bit, in more details, more deeper details. Maybe we can cover the vibration sensor. Maybe if we have a time, maybe you can cover it, maybe you cannot cover it. It depends on our times that will be given to us. So for us shabab, it's important to understand the meaning of these different terminology that we talk about it. Try to practice on them, and try to understand the variating or the very different aspects of these devices between them. Thank you for listening and waiting for the next lecture inshallah. Assalamu alaikum.